Kia ora Year 12. In this video, I'm going to go over 2 more questions from the school stats practice exam. The first one is this one, which is about a Poisson distribution, and the second one is this one about a biased 6-sided die. Okay, so let's look at question 5 first. Just before I start, this question was reasonably well done, especially the first part, but a lot of you missed the fact that we need a continuity correction in the second part. That's a really easy way to chuck 2 marks away. But I really want you to understand why we're doing continuity corrections in these types of questions as well. So I'll be talking about that yet again. Okay, so we've got a number of adult customers arriving in a shop during a 5-minute period is modelled by a random variable with a Poisson distribution and lambda is 6. The number of child customers arriving in the same shop during a 10-minute period is modelled by a distribution that's Poisson with lambda of 4.5. So before you even read the question, you know that this is probably going to be about changing the time periods, first of all. And then in the question, we see that we have to find the probability that during a randomly chosen 2-minute period, the total number of adult plus child customers has to be less than 3. So a couple of you forgot that there's a really cool feature of Poisson distributions that we proved in class, which is that if we've got x is Poisson and y is Poisson, then x plus y is also Poisson, and the lambda will be lambda x plus lambda y. So that makes this question much easier. Then all we've got to do is figure out the appropriate lambda for a 2-minute period. So let's let x be the adults. So x is Poisson with lambda is 6 per 5 minutes. So lambda is going to be 1.2 for 1 minute, and lambda will be 2.4 for 2 minutes. And we can do the same thing with the child Poisson. So it's Poisson of 4.5 for 10 minutes. It's 0.45 for 1 minute. And it's going to be 0.9 for 2 minutes. So x plus y for 2 minutes is distributed as a Poisson with a lambda of 3.3. And the probability that the total number of adults and kids visiting the shop in a 2-minute period is equal to this. So that's going to be 0, 1, and 2. So that's e to the negative 3.3 plus e to the negative 3.3 times lambda to the power of 1 over 1 plus e to the negative 3.3 times lambda squared over 2, right? So obviously some different ways to work that out on your calculator. You can take this out as a common factor first. Just be careful if you do it that way. But overall we get 0.359, and remember you need to be giving your answers to 3 significant figures. So that's that one done. Okay, now the next one says that during a sale, the manager thinks that more adults are arriving than usual. In a randomly selected 30-minute period during the sale, 49 adult customers arrive. Test the manager's claim at the 2.5% significance level. So obviously we're doing some kind of hypothesis test here, and we've got a 30-minute period, and we're just working with the adults in the distribution. So lambda for 30 minutes, based on what we had in normal times, not sale times, is going to be 1.2 times 30, right? So H naught, there's my pen gone, right? So H naught is that lambda is equal to 36, and HA is that lambda is greater than 36. And we're going to test this, but we don't really want to find this out. So what we're asked to figure out is basically what are the chances that we have 49 or more customers in half an hour if the null hypothesis is true. And that's the same as 1 minus the probability that x is less than or equal to 48. Now that's just a complete nightmare to work out. So you should pretty quickly have realized that you need to use the normal approximation to the Poisson here. And we can do that because we've got lambda being big enough. Okay, so we're going to use the normal approximation, and we're going to say that x dash is approximately normal, and it's going to have a mean of lambda, and it's going to have a variance of lambda. And that lambda is lambda assuming that the null hypothesis is still true. So what we're testing now is we're trying to find the probability of getting 49 or more people. So because we're now working with a continuous distribution, we want the 49th customer in there. So think of that 49th customer as having their own little bar in the distribution of customers. So we want 49 or this way. So we're going to find the probability that X dash is greater than 48.5, right? So there's the need for your continuity correction. All we have to do now is standardize. So we get the probability that Z is greater than 48.5 minus the mean divided by the standard deviation, which is 6, not 36. A couple of you made that mistake. Please don't make that mistake next time you do this question. And that gives me the probability that Z is greater than 2.0833. Okay, so this is one way to do the confidence interval. We've got our Z value here. There's 2.0833, and that probability works out to be 1 minus 0. All of that. So hopping over to your normal table, we can go through here. We've got 2.083.9813. Where have we got down to? Yeah. Which gives us 0.0187, and that is less than the 2.5%. It's 1.87%. So it's less than 2.5%. So we reject H0. So we need to say more than that, though. We need to say we reject H0, and then we need to put it in context. Okay, so there is evidence. I mean, no one cares about rejecting H0. We want to know about the manager's claim. So there is evidence to support her claim, or his claim. I can't remember. Okay, there is evidence to support her claim. Other ways that you could do this question, well, you don't have to do this calculation. You could simply find the Z value, right? And you could then compare that to your cutoff value for 2.5%. So all you need to do with that is you get to Z is equal to 2.0833, and that's greater than 1.96, which is your cutoff value for having 2.5% in each tail. Okay, so that's the other way to do it, and there are a couple of other ways as well, but those two are probably the most obvious ones. So that's question 5 done, and that was worth 9 marks. I'm going to look quickly now, because I've already used up 7 minutes, at question 6, which was another hypothesis testing question, which was done very well, actually. So good job, guys. I'm going to go through it anyway, because there were a few little things in here that some of you missed. So Jivan thinks a 6-sided die is biased in favour of a 6. So this is going to be a really boring question. In order to test this, she throws the die 10 times. And if it shows a 6 on at least 4 throws out of 10, she will conclude that she is correct. So we've been given the rejection region there. And this is going to be a binomial distribution hypothesis test, right? Because I've got 10 trials and a probability of a die giving a 6. So I'm going to just write out the hypotheses. So we've got P equals 6, or P is greater than 1/6. But I have to say, what is P, right? So you won't get any marks for that unless you say P, something like this. P is the probability that the die lands on a 6. It's the same when you're doing a hypothesis test for mu. You need to say, what is mu? Mu is the population mean weight of an elephant, right? So we've got n equals 10. So we reject if x is greater than or equal to 4, right? So what is a type 1 error? So that's part 1. The type 1 error is wrongly rejecting the null hypothesis, right? Type 1 error is going to be the probability that we get in the rejection region if, in fact, the null hypothesis is true. So what we're working out here are the chances of getting 4 or more 6s out of 10. So think about your dots. We've got 0, 1, 2, 3. And we're going to reject if we're up here 4, 5, 6, 7, 8, 9, 10. So that probability can most easily be found as 1 minus the probability of x equals 0, 1, 2, or 3. Right, now you need to show some working in here. Right, you need to show your binomial calculation. So it's 1 minus, and then it will be, so no 6s means 10 not 6s. And there's only one way for that to happen. then there are 10 ways to get 9 not 6s and 1 6. Oops, that should be a 6. Right, you get the idea. Then the next bit, we've got 10 choose 2. So 10 choose 2 is 10 times 9 over 2. You don't need to write that. It's fine to write 10 choose 2, right? I just have this weird thing of wanting to write out my combinations there. So that's that. Now we've got one more to do. We've got to do 10 choose 3, which is 10 times 9 times 8, over 3 times 2 times 1, times that. There. So when you work all of that out, and you need to work that out pretty carefully because some of you did screw this bit up, we get 1 minus 0.9303, which gives us a final answer of 0.0697, and again that is to 3 significant figures. So there you go, there's your type 1 error. Right, explain what is meant by a type 2 error in this situation, right? You have to answer this in context. So no marks if you just say blah, 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 wrongly accept H0. Okay, so this is what I would say here. What would we say? Type 2 error happens when the die is biased with P greater than 1/6, but result of 10 throws is 3 or fewer 6s, so she doesn't reject H0. Okay, so that would be, I think, a very good answer to that. You really have to put it in context, right? And so you should, right? Stats is meant to be communicating real life stuff. So in the last question, we have to calculate what the probability of a type 2 error actually is if the probability of throwing a 6 is as high as 1/2. So this makes the calculations quite easy, because what we're saying is when will we get 3 or fewer 6s, even if the probability of getting that 6 is equal to 1/2. So it's going to be 10, choose 10, so one way, and then we get 1/2 to the power of 10. But most of you will see from looking that what we're going to get here is, because we've got a 1/2, we get a 1/2 times to the power of 9 and a 1/2 to the power of 1. So each time we're doing it, this bit is going to be 1/2 to the power of 10. So that gives me a really simple calculation. It's going to be 1/10, oh, not 1/10, hang on, let's fix that. 1/2 to the power of 10, and then it's just going to be my Pascal's triangle numbers. So I've got 1 plus 10 choose 2, which is 45, plus 10 choose 3, which is 120, and I add all of those up, times them together, and I get 0.172 to 3 significant figures. So there you go, there's question 6 done, and I'm going to get question 7 done in the next 10 minutes, assuming the dog does not wake up. All right, have a good day, everyone, and I will be emailing you your stats scores later on this morning.